Hello everyone, my name is Nicole Vargas.
My name is Amber Gaviria.
My name is Arturo Zelaya.
My name is Eduardo Ginés.
My name is Martín Recalde, and we are majoring on chemical engineering in the University of South Florida, Tampa.
Our proposed topic consists of catalytic wet air oxidation as a form of wastewater treatment. This non-renewable resource is important for the sustainability of all living species. According to the World Health Organization and the Environmental Protection Agency, it is estimated that due to the population increase, clean water shortages might still pose an issue for future generations. Also, according to the EPA, 94,000 million gallons of water are presently being consumed in the US at a daily basis. This effect can be seen in the graph shown.
There are currently a variety of methods that can be used to treat wastewater, wet air oxidation being one of the most efficient and eco-friendly methods. Developed in mid-1950s, wet air oxidation has become a feasible method to treat effluent industrial water sludge. This method provides companies a way to release less harmful agents to the environment and the ability to recycle water. Phenol is a toxic byproduct commonly found in industrial wastewater. 1 part per billion is considered safe for consumption. Catalytic wet air oxidation has the capacity to convert 100% of the phenol in wastewater. The use of a catalyst reduces operational costs and increases the selectivity for desired reactions.
Catalytic wet air oxidation involves a process of 5 steps. The first step is that wastewater is collected in a tank with air at high pressure while trapped in water oxidizes phenol. This high pressure creates high velocities for the air, therefore turbulent flow is created. Oxygen in the air is then going to react with the pollutants in the water. In this case, phenol is going to oxidize. Addition of catalyst manganese cerium oxide suppresses undesired reaction and increases selectivity for desired reactions. Clean water is separated from benzoquinones, dihydroxylbenzenes, and carbon dioxide.
After considering the previous information and after further discussion, our team considered that a good example of a wastewater treatment plant is the Howard F. Curran Wastewater Treatment Plant in Tampa, Florida. This plant has the capacity to provide safe water to a relatively large population. Our main goal in this project was to create, illustrate, and design a catalytic wet air oxidation reactor with a processing capacity of 64.37 million gallons per day.
The methods we used were those proposed by the course instructor in the book Elements of Chemical Reaction Engineering. The reactions shown were found to model the wastewater treatment plant. The first reaction, which is desired, takes place when phenol and oxygen react to produce dihydroxylbenzene. Then, the dihydroxylbenzene reacts with oxygen to produce water and benzoquinones. Finally, the benzoquinones are reacted with oxygen to produce carbon dioxide and more water. After the 3 reactions occur, the undesired products can be easily cleaned through the sedimentation process.
This is the methodology used for the design of the reactor. The first step was to select a plug flow reactor for the catalytic wet air oxidation model. The second step was to develop differential material balances and the rate loss. The third step was to derive the energy balances. The fourth step was to select a catalyst. For this project, we selected manganese cerium oxide. The fifth step was to create the MATLAB functions. And the last step was to analyze the results.
The results and calculations were developed in a MATLAB script. Graphical results are displayed in the subsequent slides, demonstrating molar flow rate, concentration, selectivity, and temperature profiles. First, we will discuss the concentration profile versus space-time graph. As it can be shown in both graphs, the green line representing water increases exponentially as time and volume increase as well. In each case, it can be shown how the concentration of water increases and the concentration of phenol, in the blue line, decreases. This statement is supported by the graph we collected from the molar flow rate profile. The flow rate for the water is increasing and the flow rate for phenol is reduced as the volume increases.
Now, there is the molar flow rate profile compared to the change of time. Again, the same effect is shown in this graph. Water is constantly produced until tau is equal to 15 minutes. Additionally, phenol and oxygen are almost totally consumed by the end of the reaction. The selectivity profile shows the ratio of the reaction rates containing the desired product to the reaction rates containing the undesired products. Finally, the temperature profile shows how the temperature changes as the volume of the plug flow reactor increases. As it can be seen in the graph, the temperature reaches its maximum over 400 Kelvin at around 500 cubic meters.
The main takeaway from this project can be broken down into 4 points. The first point is catalytic wet air oxidation adds catalyst into the system of traditional wet air oxidation. It reduces the harsh reaction conditions, increases the oxidation capacity of oxidants, and shortens reaction time, and thereby it reduces the investment in operating costs. The second point is it is feasible to use catalytic wet air oxidation to process 64.37 million gallons per day, which is the amount of wastewater processed by the Howard F. Curran Advanced Wastewater Treatment Plant in Tampa.
As a third conclusion, we can say that paper suggests that 100% conversion is attainable. However, because of the error that some assumptions may have been introduced into the calculations, there is a 99% conversion in the designed reactor. As a fourth conclusion, we can say assumptions help facilitate the initial design parameters, but it is very important to have experimental data available to make better decisions and establish more accurate design values.
Thank you for your time. We're available to answer any questions. Here is our contact information.